and together with some colleagues you will meet afterwards, we're going to teach you a bit about AiiDA, the software we've been writing in the past years. What I want to do in this session is to tell you a bit the ideas behind it, why it's interesting, what are the things we wanted to put in the code, and why we implemented it. And then you will see today and tomorrow how it works more practically. So now it's more about the core concepts, so at least you have an idea of what it is about. Of course, at any time, if you have questions, just ask, or at the end if you prefer. So I will give this introduction, then it will be one of my colleagues, Sebastian, who will give us a short introduction of what you will need to do in the next, in the afternoon, let's say. And then tomorrow we'll have shorter introduction to each session. Okay, so what we do, and you have been here in this week or 2 weeks to work with Quantum Espresso, so you know already, I guess everybody works with atomistic simulations, want to calculate materials properties, and you know now Quantum Espresso and other tools to make the simulations. Now, however, you want to manage all the data you run, all the simulations you do. Because sometimes if you have to run 1, 2 systems, it's fine to prepare your input file by hand, write it, send it to a supercomputer, run the simulation, get the output, write the paper, and get some citations. But often you want to, nowadays, especially since there is a lot of computational power, you might want to run a lot of simulations and manage them. And as you might imagine, I don't know your experience in your research or even just in the past week, and if you start having a lot of simulations, it becomes very easily very hard to keep track of what you did. So for instance, even after a few months, you have a big folder with a lot of simulations. You have to be very careful to remember what has happened. And so AiiDA was mainly designed to provide you a tool to keep track of what you do and share the results with people in a way which is easy. So just to start with some motivations. So as you see, one of the main motivations of AiiDA, as you will see, is what is called high throughput computation. So we really want to run automatically tens of thousands of simulations. For instance, you want to calculate a given property, let's say, I don't know, some thermal property or some piezoelectric property on a class of materials. You want to do it automatically. You want to collect the results in a database, and you want them to publish a result which is global over the class of materials, not just only on one material. So this is what is called high throughput computations, and I wanted to give you a bit of motivation, maybe for some of you is obvious, and maybe you already saw these slides by someone else, I don't know. Anyway, well, the first motivation is about DFT, and I guess this may be obvious for everybody. DFT has become in the past years, in the past decades, one of the most used tools in the literature to simulate materials properties. And one way to see it, there was this paper done a couple of years ago, where they took the top 100 most cited papers ever in the whole scientific literature, so including medicine, all the Nobel Prizes, everything, and they took the top 100, and of this top 100, they made a study, and they discovered that 12 out of them are about using or about DFT. So now one can say if number of citations is really a measure for quality or the impact, but I mean, that's one of the measures we have, and this clearly says that there are many, many papers nowadays which use DFT in some way, and have cited this. So the DFT is really becoming a tool, and beside this, there are many codes. You know now Quantum Espresso, which is here, but there are many, many other codes. Some of you, I guess, know also some of the others, which allow you to use DFT, run simulations, and also be quite predictive for many of the properties you want to calculate. So you have very accurate and predictive computational engines. On the other hand, you have very powerful computers, because you have this Moore's law, which basically is telling you that every 14 months, the computational throughput through the supercomputers you have doubles. So this is a semi-logarithmic plot over time, and you clearly see if you look at the number 1 supercomputer, this is the throughput capacity, and of course it stays stable for some years because the same supercomputer is the top one. But if you also can look at the number 500, or the sum of the throughput of the first 500, which is this blue line, all of them go up exponentially. And if you want to give it more intuitively, what you would have needed 1 month to run in 93, last year, 2 years ago, would have taken only 10 seconds. So it's really, we have a very large computational power which is at our hand. We have very powerful codes, and this means that we are now able to run these high throughput computations. But there is one missing ingredient, which is how we manage all the simulations. And as you can imagine, doing by hand and creating thousands of text files by hand is very complicated and error prone. And to make an analogy, when you go in a library and you have thousands of books, you want to find something like this and know where to go and pick a book. And if, in this analogy, the books are your simulations. If you go in a computer of a researcher, very often you find something more like this, right? So you have a lot of folders in your disk, and you don't know where you have to look to get the numbers and to get the simulations. So we decided to write a dedicated platform, AiiDA, and I want to mention what are the ideas we put behind to decide how the platform should be. So these are the 4 core criteria we wanted to put in the code to make research easier. The first one, as any scientific research, I think you want your research to be reproducible. You want someone else to be able to get your data, read your paper, and be able to run, if he wants, the same exact simulation and get the same exact results. While for computer simulation, this should be easy, in practice, if you think about it, it's not so obvious. If you take a computational paper, very often it's not obvious to reproduce exact same results because maybe the version of the code is not saved and some variables are not specified because they are just thought to be convergence parameters, but in the end they're very important to converge the results, etc. So this is one first thing you wanted to have, something which allows you to very easily to be able to have your research reproducible. Second thing is searchable, because if you start running a lot of simulations, you want to be efficiently able to look for if you already run something, or to take all the results and do some data analysis on it, some machine learning, depending on what you want to do. And also you want it to be reliable, and in this sense, what I mean by reliable is both that you have some way to validate the validity of the results, but also the way in which we think, I'm saying a practical way to get reliability, is to have workflows, so codes which run the different steps of your simulation in an automated way, in a way which is known to be giving converged results. And in this way, if you want to validate, so someone else gives you a result, you can run the same workflow again on that material, and you know if the results you got is correct or not. And it's really important if you want to increase databases, because if you get data from someone else, if you also have the code to regenerate the data or to generate more data, you can, let's say you have 10 new materials you want to include, you can just rerun the simulation yourself. You don't have to rely on someone else running the simulation for you. And finally, you want to share the results. You want to be able to just give it to collaborators while you're working. You might want to, after publication, to give it to everybody so people can reuse it and maybe use for something more. And so we put these 4 criteria in what we call the ADES model, where the 4 letters stand for automation, data, environment, and sharing, which are a bit the 4 pillars around which we built AiiDA. AiiDA, so this is a paper which explains the code and this model as well. And what I'm going to do is to briefly introduce what AiiDA is, briefly tell you how every of these 4 pillars is implemented, and then we go in the other room and you start playing with the code. Just so about the code it can be downloaded from this website. It's open source. It's a very short timeline of what happened. So we start, actually, Boris Kozielski, who is part of the team, is working in MIT and Boston. He started with early version of the code, and then in 2012, we went together with EPFL and Bosch, and we started writing the current code, and it took some years. We got the first of open source release in 2015, and now the code is open. There are periodic releases, and there have been a lot of tutorials like this already. This, I think, is like something like the 6th or the 7th tutorial we do. And the code, actually, this is an old slide I realize now. We moved just on GitHub. Anyway, the code is there. You can just, if you go there, you find the updated link. You find all the code online. So how AiiDA works as a framework in general. So you can think to it as having many modules. The central core is the AiiDA API. It's a Python code. AiiDA is Python. It's written in Python, and you can interact through Python codes. But more generally, let's say AiiDA sits between you, who are the researchers who want to do the simulations, and the supercomputers. So the idea is that instead of directly connecting to one or more supercomputers you have access to, you just connect to AiiDA, which you installed, let's say, on your computer in your office. And AiiDA will take care of connecting to all the supercomputers. And basically what you do, you give instructions to AiiDA what it has to do, and AiiDA will take care of running the simulations for you. The advantage I was mentioning in a moment is that in this way, automatically, it also keeps track of all the steps you do. and it knows, it makes it very easy to know all you did and how you connected calculation between them. I go into this in a moment. So this is the general idea. The components of AiiDA are the following. As I was saying, there is a core, the AiiDA API, the Python functions you call to interact with it. And this interacts both with a storage where you store the results of a calculation, you store the inputs, etc. And it's both composed of a database and a file repository. We see why the database is important, because if you start running hundreds of thousands of simulations, you want to efficiently know and find results and say, I want results with this, I don't know, which will run on silicon with this cutoff, and you want to efficiently, in fractions of a second, fish out the data. And you want to be able to do this, you have to run queries in a database. And this interacts with plugins with both calculations, so you can run different codes. You will see here mainly Quantum Espresso, since this is a tutorial about Quantum Espresso. But there are many, many codes which are supported through AiiDA, and different type of data. So you can say this is specific data for a band structure, for a crystal structure, or just a set of parameters, forces. All of these are plugins, and if you want to think something more particular, you can always write it. As I was saying, AiiDA takes care of interacting with supercomputers. So you don't have to anymore to connect the SSH to the computer yourself. AiiDA will do it. And it's done through the daemon, which I'm going to mention in a moment. It's a process which takes care of all the automation. And you can connect to the cluster via different protocols, via SSH typically, or locally if you install AiiDA on the supercomputer. And it has plugins for many different queuing systems, LARM, SG, etc. And finally, for the user, you have different ways to interact with it, and that's what we will start learning already today. You can interact via a command line tool, which is called Verdi, which is basically a command line tool which allows you to know what calculation have been running, etc. You can interact via Python shell or Python files, and we're working on a web interface to access the data. Okay, so let's quickly see now how each pillar is implemented into AiiDA. The first one is automation. So, as I said, automation has multiple aspects. There is all the part of being able to connect to the supercomputers, being able to retrieve the calculations. But one key feature which we put into AiiDA is really the coupling of all the automation with the storage of the data. So as I was saying before, we ask you basically to go through AiiDA to submit the calculations. This will, on one side, make it easier because you don't have to SSH to the supercomputer, and many operations can be done automatically. But most importantly, basically what you do when you want to submit a calculation, you first store through Python calls, you will see what you want to do in the storage first. And then the daemon, which is a Python process which runs in the background, we just go in the database and try to understand what you want to run, create the input file for the code, and run it. It will not ask you anything. So if this basically implicitly forces you to specify everything you need to do to run the simulation. Because if this process is able to run the simulation for you, it means here you have all the information you need, all the inputs. You cannot forget about a parameter. You cannot forget about a file. And so the other advantage, so this gives you reproducibility of single calculations, because if you have the input, you can just run it again and run the same simulation again. And also helps a bit because it gives you a uniform way of specifying how a calculation, the inputs of a calculation, and you can do easily queries. Once this is done, the daemon takes care of all the submission part, as I was saying. So we'll prepare all the files. We really create the input file, the text input files for Quantum Espresso that you have seen. We'll submit it to the scheduler. We'll wait for the scheduler to finish. When it's finished, we'll retrieve the calculations, the results, parse them, store the results in the database, and set the calculation to finished. Okay? This is automatic, and tomorrow, later you will see, but basically you just have to write a file where you basically, if now you know Quantum Espresso, you will recognize here in a different format the name list, control name list, calculation SCF, the cutoffs, etc. You have to specify something more, of course. You have to say how long you want to run, how many CPUs you want to use. You do this, and at the call here, basically everything goes through the daemon, and the daemon takes care of all the creation of the input file, etc. And by just changing the name of the cluster, that's another advantage. You just change the name here, and AiiDA will do the same thing on a different computer, even if the scheduler is different. So it will know you have configured this to say cluster 2 has a different scheduler. It will create the correct input file for the other computer. So this is about automation, which is a bit useful, but let's say in the end, if you have been working in this field for some time, you have your own script. So this is useful because it's always the same, independent of the simulation you want to do. But that's not the key part of AiiDA, I think. The other important part is data. And the question we asked when we started is we want to store in the database, or at least somewhere in the computer, which calculations we run to get to a final result. Now, the point is that if you think to it, you almost never run a single calculation, get the result, and that's what you want to publish. Almost always, you have to run a sequence of many steps. You want to do an SCF, a relaxation, then you want to do maybe an SCF, you have to do phonons, you want to do some post-processing, etc. So what really cares is not just the single calculations, but also how they are connected together between them. So you want to preserve and store not only the calculation, but their connected structure. And how can you do it in a computer? Well, the idea we took from what is called the open provenance model, which is just in the end, it's intuitively simple. You can think to any calculation as a black box, which takes inputs and returns some outputs. For instance, if this is a quantum espresso calculation, this could be the input crystal structure. This could be the set of parameters you would put in the name list and the k-points. And in the output, you get the relaxed crystal structure and some parameters like forces, total energy, etc. So this is a very generic scheme, which is valid for any simulation. The trick is now you can think to any output to become an input to a new calculation. And what you end out is something which is a direct acyclic graph. It's directed because you have arrows, so from structures, from data, you go to calculation and to the outputs. And it's acyclic because, of course, an output cannot have been an input to the same calculation. And you see, by having this, you automatically store, let's say, if you have a final calculation here, you know it was produced by this calculation with these parameters, but the input structure was coming from a relaxation with these parameters from the initial structure, let's say from an experimental database. So you really keep what is called the provenance. So you keep the history of your data, not only the last calculation which produced it, but really how you generated it from the very first structure you started from to the very final result you want to publish. So I hope I kind of convinced you that if you store things in a graph, you automatically keep track of the provenance and all the history of the data. Now the question is how you store it in practice on a computer. And how can you query for it? How can you ask which calculation will run with this structure and had as an output positive phono frequency? And so just 1 or 2 slides very quickly to just give you an idea. The idea is that you want to store somewhere, in our case in a SQL database, the nodes, the links between them, and every node will have a lot of properties. For instance, if it's a calculation, you want to store the wall time, you want to store the computer in which it runs, etc. But if it's an output, you want to store the forces, you want to store the energy. If it's a structure, you want to store the crystal coordinates, etc. And so there is a, let's say, I don't want to discuss it here, but there is a way to store very flexible properties, really key value properties you can store for any key, any value, and then you can efficiently query for it. I won't go more into details. If you have questions in the next days, today and tomorrow, we're very happy to discuss more in detail, but it becomes a bit technical, so maybe it's boring for someone. The third pillar, so the first two, automation and data, were more low level, how you automate the simulations, how you store the data in the database. Now you have 2 more user level pillars. The first one is environment. And if you want this, try to ask you how easy it is to use AiiDA and if it's better or it makes some advantage to use AiiDA over some scripts I could write in Perl or Bash, etc. And so I collect in this slide a few aspects of things we try to put into AiiDA to make it easier for researchers. The first one, we chose a language which starts to be relatively standard in the community, which is Python. And anyway, it's a language which even if you don't know, if you read a simple Python code, you typically can understand what's going on. So it's not a very complex language, but still is very powerful and also has a lot of modules. So you can really, once you learn it, you can use it for everything, basically. The second part we learned tomorrow morning is we developed a way to run queries in the database, which is essential to get quickly the answers, using a language which is independent of the database. So we don't ask people to learn SQL or other languages because this would be, I mean, many people are not interested. We just have an easy way to do queries, say, to get information about nodes and their connectivity. But we will see this more tomorrow, so I won't stop here. We're working on a seamless user interface, so we already have the command line with C, and you have a way to produce graphs, etc. And we are working on a web interface. And most importantly, I think there is a very extensive documentation online. You can go there on this website, get the full documentation from when you install the database, how you install AiiDA, and how you run simulations. And we are doing tutorials, so these tutorials are online. We'll also show you later the link. Basically, what the tutorial you're doing today will also be available online on a virtual machine. So if you later on, or your friends in the next months want to learn about AiiDA, they can just go there, download the virtual machine, and they can do the same, basically the same tutorial you're doing today and tomorrow. Another important aspect, however, is that we didn't want to have AiiDA very specific to the applications I might be interested or my colleagues might be interested. So we didn't want it to be only for quantum espresso or only for a specific scientific application. But we wanted it to be generic and modular, so we developed all the functionality via plugins. So for instance, in AiiDA, you can choose plugins for calculation, so how you generate the input files for a given code. And there are many codes which are already supported. How you parse the data, so once the code finishes, the parser will take care of reading the output, converting this information which can be stored in the database. The data, as I was saying, there are different types of data you can use as inputs to calculations, and many of them are, basically they are all plugins. So for instance, crystal structure is a type of data. The advantage of having type of data is that a crystal structure will be able to be shared between Quantum Espresso and VASP and Flare and other codes. So by having a plugin, you can define new ones, but also you can define things which are more generic than a single code. And also more at the lower level, you have plugins for transport, so how you connect to supercomputers via SSH, locally, or via other protocols. For the schedulers, so which schedulers you want are installed on a supercomputer. Or for instance, we have a set of importers and exporters from databases of crystal structures, for instance. We have already ICSD, COD, and a few similar databases. And again, if you know of an additional database, you can just add a new plugin, and you can then download crystal structures from there, or even in the case of TCOD, you can even upload your results there afterwards. So this is more about usability, but the other key feature that you will learn about tomorrow afternoon probably, or late morning, is about workflows. So I think I already discussed how important it is to keep the connected structure between different calculations. You always run sequence of calculations, and you want to know how we went from one to the other. By storing in a graph, as I showed you before, basically this is a log, a history of what you did in the past. Okay, you go in the graph and you see, okay, I ran first this, then this, etc. But this doesn't necessarily make it easy to run it again. I mean, if you want to run exactly the same one, it's fine. But if you want to just follow the logic and you have some convergence loop, you want to have the Python code which actually ran that simulation and decided, for instance, if to do a new loop or not, which parameter to use, etc. And for this, you need workflows. And it's really about writing code which allow you to encode what the logic you as a researcher would do. So you know, for instance, that you start with some convergence, and then you look at the numbers and you decide which cutoff to use, and then you run the SCF, then SCF, and then maybe you run the phonon with some parameters, and you have some knowledge about why you do it in a specific way. And maybe the code crashes, and you know that looking at the error code, you know what you have to change. You might want to increase the number of steps. You want to change the mixing parameter. All these things very often can be written in a code. It takes a lot of time, but it's something that can be done, and allows you to run in a high throughput many calculations. Actually, if you want to run high throughput, it's essential. Because if you imagine even to have a 1% failure rate, so 1% of a calculation crash for some error, and you have to manually inspect them, if this is the case, when you start running already 10,000 simulations, it means you have to manually check 100 calculations, which is a lot in the end, if you think, and decide what to do. So it's really important that these workflows are kind of turnkey solutions. So something you give an input structure, you tell what you want to get, and they're able, as much as possible, to fix errors and to go around potential problems. In order to do this, we developed, it's Python, but it's some tricks to be able to allow you to easily preserve the provenance, the link in between different calculations. And one way you will see tomorrow, but just to give an idea, imagine you want to do this, really simple example. You won't use AiiDA for this, of course, but just to give an idea of what's behind. You want to do a calculation where you want to do 3 + 4 and then multiply by 5. So you define a function sum, which just returns the sum of the two numbers, and a function multiply, which makes the product of the two. And then you have a function which does this combination. So it sums A and B, and takes the result and multiplies it with C. Now, if you just run it, you get the number in Python. But this is not, of course, stored anywhere in the database. If you want to store in the database, in AiiDA, we just add this decorator. So even if you don't know what a Python decorator is, just think you add these 3 characters on top of each function you want to store. But just doing this, when you run, every time you run this simulation, this function in Python, this gets stored in the database. You will have this add multiply wave function, work function, which gets as input A, B, and C, 3, 4, and 5. And this calls first sum with A and B, and the result, which is called sum, is 7, okay? And then it also calls the product of the result with 5. So the result here is 7 times 5, see? And returns 35, and this is the result, okay? So just by adding 3 characters, basically, you are able to store in the database what is called the provenance. So you know this final result was obtained through this. This was the input, and these were the inputs of this preliminary calculation, and who called who. So again, nobody should, I think, even try to run the sum and store the database but imagine these now are relaxations or phonon calculations. But just wrapping these things in this way, it's easy to keep track of what you did. This is for simple calculations. So this is more suitable when, you, for instance, you get as an output a crystal structure, and then you want just to change the volume. So you can do this quickly in Python. And store you want to do an equation of state. So from a given structure, you have to do different volumes to get the equation of state. And you want to keep track of, from this calculation, changing the volume by this factor and getting the output. So I keep track of the history. If you want to do something more complex, you will see tomorrow there is an extension on this language, which allows you also to, as I said, okay, keep automatically tracking of what you do. Run both in serial and in parallel. So if you do an equation of state, for instance, you can run all the steps independently. And then wait for all of them. And AiiDA keeps track of waiting for the calculation to finish, to run the next step, let's say a fit. You can look at so this basically gives you a way to run again the same simulations. And importantly, you can nest work functions and reuse them. So it means that you can write a workflow or a work function for some basic operation, and then you can give it to someone else who can use it for more advanced simulations. And I make an example why this is really important. This is a workflow which actually has been implemented by some colleague of us, where you just want to do something very simple. You want to relax a structure, get the dynamical matrices with the phonon code, calculate the interatomic force constants in real space, and then Fourier interpolate them back to get the full phonon dispersion. Now, when you do this, maybe if you want to do it in general, very often you want to start maybe with some loose parameters to get roughly the correct structure, especially if you start from some structure which is not necessarily near the minimum, and then do multiple relaxation to really get to the real minimum with very tight parameters. And each of them will be maybe consisting of many starts, because maybe the structure is big, and you don't fit in the wall time of the supercomputer. And again, as I was saying, maybe something fails. Maybe the diagonalization fails, and you want to change the diagonalization algorithm. So similarly, for dynamical matrices, you might want to calculate each Q point independently and then collect the results. Well, for instance, instead, these steps typically are very fast. You just have to interpolate. This has been implemented with each level. You have a workflow which is nested. So a person which is very expert of PW could write this. This just says, I give you a structure, please give me the relaxed structure, okay? And this maybe has to know about restarting, about what happens if there is an error, etc. If I have this, which basically tells me, if you give me a structure and some parameters, I'll try as much as possible to give you the final structure. You can put in some higher level workflow, which just takes the final structure and relaxes it again with different parameters, and put it as a step in a higher level workflow. So this really allows you to make modules and distribute them and share not only the data, but also the code. And this is important because, for instance, then this basically is something which, given a structure, will figure out the converged structure and give you the phonons. You can then take this a kind of black box and use it in some other project which just needs the phonons. So this might run a lot of simulations, and as I show in a moment. You don't care. You just take this workflow, give the structure, get out the phonons and use it, for instance, to do thermal properties. And just to give you an idea, the idea is really to get some kind of turnkey solutions where you start with just a few 10, 15 lines of inputs where you say, basically, the k-points density in k-space. If you want a tight convergence, which is documented what tight means, what is the structure, what is the set of CO potential you want to use, on which machine you want to run, some basic parameters like the cutoffs and the parameters for the phonon. When you run it, you get a very complex graph. And if you zoom, you can understand a bit better maybe what it contains. You see, basically here you have the first, once you know, it's easier to understand, and you will play a bit with this, we understand better. But this, you have all the inputs of the PW calculation. The output structure is sent to different calculations for each Q point. And the final result is collected, and you get at the end, for instance, this is the Q2R calculation, which gets the force constants in real space. And everything is trackable. So at the end, if you get this graph, which of course you can zoom, you get the final phonon dispersion. You can go up and see what was the initial structure, which parameters the workflow used. And this is being used, for instance, this was one of the modules used in this project, which has been published on the archive recently, which was to use to, for instance, discover 2D materials in a 3D database. So we started from a three-dimensional database, actually both COD and ICSD. We looked with a geometrical algorithm for layered structures. And these were all tracked with AiiDA. So we really know from which database entry we started, which algorithm, which threshold we used to get the layers, etc. And once we do this, we send this through these workflows to calculate both relaxed structures, but also other properties like phonons, etc., binding energy, etc. But this is used by many projects. Here, just listing a few of them. It's really a non-exhaustive list. I just showed this mainly to show one thing. So I've been speaking a lot about high throughput. And of course, if you do high throughput, it's useful to have AiiDA because it helps you managing all the simulations, keeping track of everything. But even for projects like this one, for instance, which is phonon-phonon scattering, this is really very expensive third-order derivatives. This is really not high throughput. You do 1, 2 systems, and a very small system, that's it. Still, people use AiiDA because it allows you to keep the history of what you did. So after 6 months, you go there, and it's easy to remember what you did, and AiiDA keeps track of the data you stored. The final pillar is sharing. And as I say, the idea is that you might want to share data with people. So one case is you publish your data, your results, and you want to give these results to other people so they can reuse them, or even try to rerun them or see exactly what you did. Or maybe even before publication, I'm working with a colleague and I want to give him part of, say I'm in charge of doing the relaxation, and then my colleague is in charge of doing the phonons, and I want to give part of the data to him. And so the idea we put is, instead of making a central cloud server where everything runs there, but then it's tricky because maybe people don't trust the cloud, etc. And maybe also you have access to your own computational resources. AiiDA is a code you can install yourself and run locally. You have your own data. But then, when you want, you can share parts of the database with other people. And so I can share part of it with a colleague, but a different part with a different colleague. And also, with these plugins you put in place, you can also then contribute to cloud repositories if you want to. We are working a lot on Materials Cloud, which a version of which will be out in April, which is a web interface. And this is a cloud service instead. Basically, the idea is that if you run calculation with AiiDA, and then you want to publish and you don't have a web service to publish them, you can just push them there, and they become public. People can access them. But also, in the same time, we also provide you guys a web interface so you can even look at your data through the web interface. So this has 2 advantages. You can look at your own data through the web interface, but also you can have a cloud system where you can put your data and say to people, this is the data, this is URI you can access to. And on this web interface, we want to put a kind of app store model where basically it's easy to go and click and get components and plugins for AiiDA. So you can have plugins for specific simulation codes, pre-configured information for specific clusters. So say if you work at a specific cluster and it's already there, you can just click and the computer gets configured for you. But most importantly, for the workflows. As I was saying, let's say we make a workflow for the phonons with Quantum Espresso, and then you can take it, reuse it for doing thermal transport, and then you can even push it back here if you want to share the code with other people. So it's really, I mean, the message we were really trying to push here is that we don't only want to share the data itself, but also want to share the code which allows you to generate data. So this more or less brings me to the conclusion. I just want to acknowledge all the people who have been working on this in the past years. So this is the current team, and you will see some people. So actually, today and tomorrow, it's me, Fernando, Leonid, Sneal, and Sebastian, who are going to help you for the tutorial. And actually, I have also to thank all the people who have been helping in this. There are people who have written a lot of plugins, people who have contributed in different ways to the code. There's really a lot of people who are working on this, and if you're interested in contributing, we are very happy to accept your contribution. Just to mention the more say the acknowledgement part, beside the people, we also have to acknowledge the funding. So we have two fundings. One is Marvel NCCR, which is a Swiss project, which is financing more than 30 principal investigators in different institutions. And MAX, which is a European center, which is also financing the research. So Marvel is more about discovering new materials. So it's one of the main funders also of the people working on AiiDA. And MAX is more about going to the hexascale and providing reusable workflows. So to conclude, I wanted to give you a first preliminary idea, flavor of what AiiDA is. We're going to see everything in detail, and hopefully by tomorrow, all what I said will be more concrete and clear. But I wanted to re-mention these 4 pillars, which really AiiDA is built around. The first one is automation. So on one hand, you really have a daemon which takes care of connecting to the schedulers and the supercomputer and taking care of all the automation part. And everything is abstracted into API. And this automation is coupled to data, which by storing things as a graph, allow you to keep track of the provenance and give you reproducibility of your research. Allows you also to make easy queries because it's a database. All this is in a flexible platform which allows you to have plugins to extend it with your own codes, your own workflows. And finally, allows you to share both your data and your code with collaborators to create a kind of ecosystem where really people are encouraged to share the code and do more research in the end. These are some links, and that's it. If you have questions, I'm very happy to answer them.